Now we're going to talk about vector fields. When we were thinking about vector functions, you saw a vector structure that was populated with little functions of a single variable, such as t. And as that one variable changed, we drew different vectors, and that set of vectors, as it was being generated by changing values of t, drew a curve in three-dimensional space. This is an example of a vector field. A field like a field of corn. Everywhere you look in Indiana is corn. In a vector field, everywhere you look in space is vectors. It's not just a curve. Every single point in space is assigned a vector based on the coordinates of the point. If we went to the point x equals 72, y equals 1/4, and z equals the natural log of 87, those three values could get placed into these little recipes in the components, and we would create a vector which is now assigned to that point. So that is a vector field. It is different than a vector function. With vector fields, we can do a bunch of operations. So I'm going to introduce you to the most awesome thing in math. Like, you're in Calculus 3, you have now gotten to where you get to do the super fun stuff. This is the coolest thing that there is in math. It is the differential operator, which is sometimes called del or nabla because of the shape of the symbol, the upside down triangle. It is an operator. Operators are things that have jobs to do. You're like, I've never used operators before. Well, the heck you haven't. You've done square roots. The square root is an operator. It doesn't make any sense when it's sitting there by itself as a square root sign. It only works when it's attached to something. That's an operator. Derivatives by themselves are operators. Antiderivatives are operators. They're symbols or mathematical operations that have a job to do. This happens to be a collection of three operations in a vector. And it's called the differential operator, or the vector differential operator. Most people are going to call it nabla or del. We can do different things with this because this vector field is a vector. This operator is a vector. What are some of the things you can do with vectors? Well, you can do their dot product. So if I take a dot product of the vector differential operator with f, I'm going to get the derivative with respect to x of this component. I mean, it's a dot product, right? It's just this, quote unquote, times this, plus this times this, plus this times this. You've generated a sum of three derivatives. The x derivative of that component, plus the y derivative of that component, plus the z derivative of that component. That just makes a garden variety function. It's not a vector function anymore, it's a scalar function. That's called divergence. We could do a cross product of the differential operator with the vector field f. That would give us a new vector field. You'll see examples of these. I'm just introducing the terms and the notation. And if we have a scalar function in hand, like f equals e to the x plus e to the y plus e to the z, whatever it is, if we let the differential operator act on f, we will generate a vector field. So what's going to start happening here is you're going to learn these operations. They are pretty simple. You'll get used to them really fast. You're going to have a soup of, oh man, this thing combined with this thing in this way generates a scalar function, but this here produces a vector function. This produces a vector function, which brings us back. There's a whole bunch of different ways to go, and that's where you'll have to be super careful to make sure that if you do an operation that's supposed to produce a vector field and you come back with a scalar function, that's bad news, or vice versa. So you'll have to mind the details. I'm going to pause, and I'm actually going to do these calculations for that vector field, and then you can head for the notes and the examples to dig in a little more deeply. Here is our vector field f again on top of a fresh sheet of paper. Let's calculate the divergence of f, which is the dot product between the operator del or nabla, the vector differential operator, whatever you want to call it. Remember that del itself is just the collection of differential operators with respect to each coordinate, so dx, dy, dz. And we're going to do the dot product with f. Now, f is kind of messy, so I'm going to be really lazy and not write it all down together because it's a dot product. This is easy, right? So we can expand this as the derivative with respect to x of that first component plus the derivative with respect to y of the second component. Remember, it's just a dot product. So this times that plus this times that plus this times that. It's just here the times, quote unquote, is the connection of this operator to that thing, right? This operator d over dx doesn't do anything until you stick it on something. So we're not really multiplying anymore. We are allowing this operator to act on that component, this operator on that component, and so on. By the time we get to the third, d over dz, we get that. So there, that's that dot product expanded out. And now, hey, these are partial derivatives, and they're easy partial derivatives, right? You should breathe a sigh of relief at this. That one right there, that's just y. And this second one right here, that's just 1. And this one right here, that's just 2z. And so the divergence, that's the word that describes this dot product. The divergence of this vector field is this scalar function. So again, you're going to have to start keeping track of, here's a vector field. I can do different things to it that generate other vector fields or scalar functions. Which is which? Make sure I'm tracking it properly. Okay? But divergence creates a scalar function out of a vector field. There are physical interpretations to all this. You'll see some of that in the notes. I don't want to overload this just very basic introduction. Now I'm going to do the curl, which is so much more fun. We're back to do a curl. It's the same vector field as before. Now we're going to do the curl, which is del cross f. Cross product. You've done this, I hope, because otherwise this won't make any sense. To do the cross product, you're saying, well, this doesn't even have real things in it. It just has those operators d over dx, d over dy, and d over dz. How do I do a cross product with those? And the answer is, well, you do it the same way you would do any other cross product. You set up the components of the two vector quantities, the first one and the second one, in a 3x3 grid. You have the I, j, and k waiting to collect the results in their proper vector form. And just like with the divergence, when we match these up, right, with just regular vectors, this becomes a product of this times this minus this times this, for example. Here, it's not really a product, it's an operation. So this operator will get to act on that. This operator will get to act on that. Whatever combination you run into, that's what you get. And so I have a template waiting for this cross product. So to do the cross product, the first thing we do is stop at this entry I, and we ignore the entries below it, and we take the little minor determinant in the rest of the block and lay that out. And so we do this little minor determinant by doing this quote-unquote product minus this product. Well, the derivative with respect to y of x squared plus y squared plus z squared is 2y. And then in the crisscross direction, the derivative with respect to z of e to the negative x plus y, that's 0. Well, that's cool. Okay, then we go to our friend j, and we ignore that column, and now we do the crisscross connections. Derivative with respect to x of this, now that's a 2x, minus the derivative with respect to z of x plus y plus z, that's just a 1. And remember, in this determinant form, it's plus, minus, plus, so I've got those signs already waiting there in place. And then we go to k, block out that column, and now we do this connection. Derivative with respect to x of e to the negative x plus y is e to the negative x. And then this connection, derivative with respect to y of xy plus z, is x, and we're subtracting this connection minus that connection. And then, if you like brackets instead of IJK like I do, you can recollect this business in brackets. This I'll write as 1 minus 2x, and then here, there's really nothing better to do with it. Like that. And there you go. That's the curl. And again, you'll see what we might do with the curl. There are criteria that this vector field might or might not fill based on the result of the curl. You might imagine that if you're working with vector fields and you do a divergence or you do a curl and you get 0, something interesting might be going on, and that is the case. That's all in the notes. This is just the opening salvo of operations. I do want to mention this whole IJK business again, since they showed up in the process of doing the curl. The vector fields I've shown you are written in their bracket format. You might see a vector field that's given in the IJK format. Like I could write this vector field as xy plus z times I plus e to the negative x plus y times j, and so on. Don't let that get in your way, right? It's just two equivalent ways of listing vector content, either in the brackets or attached to the unit vectors I, j, and k. It doesn't change anything about what you do. So be ready for both formats. If something is started in one of those formats, you probably want to keep it in that format just for consistency. Last thing up, I'm going to do a gradient. The last thing here, and this is sort of a preview of something that's not even in this first immediate topic dealing with vector fields, but it goes nicely with divergence and curl, and it's an operation called the gradient. The divergence and the curl are actions that we do on a vector field. The gradient is an operation that produces a vector field. So let's suppose we start with a scalar function like sine of xyz. It's just a garden variety function that produces a scalar number when you plug in values for x, y, and z. The gradient of this function is what we get when we let the del or nabla operator act on it. This is not a dot product, it's not a cross product. It's just like a scalar multiple. You have a vector times a scalar. Now you know that when you do a scalar times a vector, you just take that scalar and multiply it through all three of those components. And so you would, of course, write the first component this way, correct? No, do not do that. Remember that the d over dx, the d over dy, those are operators. They have a job to do. You don't put a square root sign after the 16 when you're doing the square root of 16, do you? If the answer is yes, I don't know what to tell you, but you know not to do that. So similarly here, don't put a derivative operator after the thing it's supposed to be acting on. Put it before. So this is what our gradient looks like, and then each of those derivative operators has a job to do. You can pause this if you want to consider the details of those derivatives, but they're not difficult. And ta-da, we've just taken a scalar function, let this fun new operator act on it, and it produces a vector field. And so that's called the gradient, and there's a whole lot of places that this goes. If you've taken physics, you're familiar with things like the electrostatic potential function or the gravitational potential function. Those are scalar functions. Their gradients are the things that produce the vectors that describe gravitational and electrostatic force. So we are in some super powerful stuff here, but you have to start understanding the fundamentals to begin with. One other fun place this goes, can you tell I like this stuff? We took a scalar function and we just produced a vector field. Well, we just saw a whole bunch of things you can do with a vector field. So like divergence and curl. So can we make combinations of all this stuff? And the answer is, oh boy, can we? Take a scalar function, produce its gradient like this, and then take the curl of that gradient. What's going to happen? Well, interesting things do happen sometimes. And some of the questions that you're going to be faced with are just taking all these operations like gradients, divergence, and curl, and applying them in different orders and just trying to figure out what operation is even legal to begin with, because some things produce vectors. Other operations expect vectors or expect scalar functions, and so you have to make sure that everything connects properly. or it isn't going to work. Fun stuff. I hope you like it.